Hello and welcome to all the viewers. In this video, we will going to see the pressure vessel nozzle shell junction analysis with submodeling approach. So if you see, this is nothing but the schematic of horizontal pressure vessel, and this is what the local nozzle N1. So this is shell model, and now we will going to do a simulation for the solid nozzle shell junction simulation. So we have already covered the first part, that is like a pressure vessel analysis using shell modeling approach, and now we will going to use the same model to perform the submodeling. So this slide represents our problem statement. So this is nothing but our problem statement of our first video, which we already completed, and that is uploaded in our portal. So you just go through that. First you can finish that simulation, and then now we need to analyze this respect to nozzle, that is N1, for the above loading and boundary condition. So when we talk about submodeling, there are so many uses of submodeling. Suppose in some of the cases you need to analyze any particular nozzle or any particular junction. Suppose you need to analyze this pipe connection, this nozzle connection. Sometimes we also need to analyze some saddle portion. So in that case, instead of analyzing a complete vessel, you can use this submodeling methodology, which is quite useful and which is most widely used in the case of oil and gas industry, or you can say the plant in equipment simulation. So now there is a lot of advantages, such as like you can reduce the simulation type. Then next you can use the global model result, and you will get the more accuracy on a local model. Then if you want to do further more changes, suppose you analyze the complete vessel and now you found that this particular nozzle is filling. So in that case, if you want to add some reinforcing pad, if you want to add some welds, so instead of analyzing the complete vessel, you can analyze the single part or any part which is filling by using the submodeling approach. So we already covered one video in our portal. Like if you see, we already uploaded this video, that is submodeling of the top side model. So, and also we explained what is the principle behind this submodeling approach. So you just go through this video also, and you will get the complete insight of what is submodeling, what is the basic principle of submodeling, and this is completely different than our present video. So you will come to know how to do a simulation when we have a beam connections. Okay. Now if you see, our present video is completely different than the previous submodeling video. So now without wasting time, we will go to our ANSYS, and there we will discuss this present simulation. Now if you see, this is what our ANSYS Workbench analysis did. So you just need to drag and drop your static structural simulation. So this is what the simulation which we already performed in our first video, and you just refer our YouTube video and complete this simulation part. And then in order to perform the submodeling, there is no need to have a separate you can say that analysis system deck, but you can simply duplicate this. Right click here and you can simply duplicate, and then you will get the another window like that, and then you can note it down like submodeling or whatever the nomenclature you want. Okay, now once you duplicated your deck, then you need to go to inside your SpaceClaim. So I will just show you. So now if you see, I had already created a local model, so I will not going to take much more time for that explanation. You just refer our another video where we explain a SpaceClaim how to do designing part. So now if you see, this is what the complete shell model part. Let me make it shaded, and this is the shell model part. So, and this is the solid model which we will going to analyze in a present submodeling simulation. Now if you see, in order to obtain this model, you just need to you can go to the design, and then you can use this spool option. You just spool that and increase thickness, whatever the thickness of your vessel, accordingly up and down on both sides. So you will get this respective solid model part. Or else you just model that in a different you can say the software, and you just import that file from assembly, and here you can have an option of importing your respective file. But it is better to have a same file from the existing analysis deck. Okay, now this is what our simulation model. Let's hide other. This is what simulation model. I already hided the unwanted part, and now we will going to analyze this respective model. So let's go further to Workbench. Okay, now we are further inside the Workbench. Now just double click on a mechanical part. So now if you see, our model is open inside the ANSYS mechanical. Now the very first part, so as discussed in a first part, you just need to follow the same. We are going to use structural steel as a material. Now we will going to analyze this respect to nozzle. So it is better to have a quite finer mesh when we talk about the submodeling approach. Okay, so at present, as this is just the explanation video, so I will just go with the global sizing. So let's see. So now if you see here, the global size is like 44.688. So it will be very coarser, you can say like that. Or let's see if we had given few. So these are the global mesh options which you will find in your model. Okay, now let's define the local sizing. Right click, insert sizing, and here you can define whatever the sizing you want. So we already created a lot of video for a meshing, as well as we also created how to do a particular map mesh for a nozzle shell junction. You just go to our channel page, and there you can refer how to create a finer and good quality mesh. Okay, so at present I will just explain the submodeling methodology, so I will not going to cover that part. But let's go with some finer mesh so that we will get the more adequate result. Okay, that's it. It is also okay for our present simulation part. Now in order to do the submodeling, you should have the results from the global model. So for that, you can go to here, and now if you see, we need to connect this solution part to the your submodel part. So for that, you just need to drag like this, and you can put over setup part. So now what is happening over here, like this solution. So basically the results we are carrying inside the submodeling deck. So right click and then refresh. So when you refresh this, you will find the submodeling option inside the mechanical. So you can see over here, this is what the submodeling options. Now here right click, insert, and here you have different options to apply, like boundary temperature, cut boundary constraint, remote forces, even cut boundary remote constraint. So let's go with cut boundary constraint. You can use anyways. So any options you can use, and you can define the cut boundary. So basically this is the cut boundary. And also very important thing, when you are doing submodeling, it is better to keep some distance, or you can say the length. So ASME recommend like a 2.5 square root of RT. So basically the length should be greater than 2.5 your inside radius into thickness. Okay, so the formula is like 2.5 square root of RT, or even just as per your engineering judgment, you just need to avoid the high stress region and increase the length, or you can say avoid the discontinuity or avoid the stress concentration. So that's why it is better to keep some margin for the length portion. So now before importing your results from the global model, you need to click over here and inside the detail you need to see the transfer key option. So basically it recommends us like whether you are using solid to solid or shell to solid. So this is what the our purpose of a simulation. So we have a global model which is the shell model, and we have a local model which is the solid model. So in that case you should use the shell to solid. And also if you have number of load case, so you can define the number of load case like all, range. When you have like in first load step you have applied nozzle load, in second load step you have applied thermal loads, and in third if you have applied your pressure load. So in that case this source time is useful to define the respective step. Okay, and the remaining things are like you can keep program control. So this is not exactly, suppose if you want to deviate your cut boundaries, or your model is deviated or rotated or transfer, so you can define even that respective coordinates on this rigid transformation section. Okay, and there are a few more like if you want to create name selection, so I will suggest you all this except this transfer key option. You can keep all the option as a program control. So this is very important thing. You just need to use shell to solid. And then now let's try to import load. So when you import, you will find that whatever the boundary constraint from global model will going to come in a local model. So you can see this is what the your cut boundary constraints which we imported from the global model. Now that is what the advantage of this. So we are using a result of a global model on a local model. Now the next thing, you need to further apply the local loading condition. So basically let's apply the pressure which we have. Let's extend to limit, and then you can apply, and this is what if I'm not wrong, this is 3 megapascal. Okay, this is 0.3 megapascal, and there is one more boundary condition. So you should apply when you do the local modeling, or you can, the correct way you can apply here the compensating pressure. Okay, but we will going to follow the load which we applied, that is just a constant, that is frictionless support. So you just need to calculate the compensating pressure. So we had already explained what is compensating pressure, what is thrust pressure. You just go to our blog page, that is www.graphengineering.com, and there you can refer what is compensating pressure, how to calculate that. Okay, so let me okay, so I am right now inside our blog post. So if you see here, we already explained like what is compensating pressure, what is compensating force, what is thrust pressure. So also explained the analytical formula. So you just go through that, and also we explained. So here it is like 5 square root of RT. So I told you like 2.5 square root of RT. So based on your judgment, engineering judgment, you can consider that. Okay, so this is the distance. This is the specific part which we analyze just to understand what is thrust pressure and compensating pressure. Okay, so you just go through this blog post and clear your doubts. If you have any concerns, let me know your comments. I will be there to reply. Okay, now this is what the pressure, this is what the frictionless support, and this is the imported boundary condition. Now we just need to solve the result. So until that, let's go inside the, and here try to open this model. Okay, this is what the our first model result. So when you cross check the accuracy of your submodel, you can hide other bodies and zoom to fit, total deformation, adjust to visible, click on. So this is the shell model. You can see like, so in submodel also you should have a similar kind of deformation. Okay, so that is what you can cross check this result with your submodel. When you thick this part, you can also check the thickness. And now let's go our submodel. So now if you see, our simulation is completed. Let's extract the deformation, let's extract the stresses and evaluate the results. Now if you see the total deformation, now you can see this is what the deformation from global submodel, and now this is the deformation from. So if you compare both the results, you will find that this is this our global model and this is the submodel. So likewise, you can cross check the accuracy. Now let's show all model, adjust to visible, and this is what our submodel. Now let's check the stress values. Now stresses are somewhere, you just forgot the stress, and the cross check the stresses at the junction 46 like this, 72 from inside, so which is also the quite. Let's do one thing, this important constraint will basically vary when you, if you do proper coarse mesh over here, and then you will find that this localized stress, the maximum stress will be gone. So you can do this exercise at your end. I will just explain the furthermore the advantage. What we will do right now, if you see, our stresses is like here 70 megapascal all around. So let's do one thing, let's try to increase the pressure. What will happen? So now if you see here, in a global model, we observe that the stresses are only 79 megapascal and for the given pressure conditions. So suppose there is a case like your particular vessel you need to analyze, and which is having a higher pressure vessel, or you can say that it is failing under the yield limit condition. So in that case, you need to do some reinforcing. So you can provide the reinforcing pad, you can even provide the weld over here. So in that such a scenario, instead of doing the complete vessels simulation, you can do the you can use this submodeling approach, which is quite feasible, and also it will save a lot amount of time, because when you do a complete FEA for a whole vessel, it will take time, it will take your efforts, as well as it will take the huge time for the simulation. But with the help of submodeling, you can just use this, perform the complete simulation with the coarse model, or we can say that with the coarse mesh, get the result, and then you can do the finer mesh for your local submodel. Now let's check. Okay, now our simulation is performed. Let's check the deformation might be increased, and also check the stresses. So now if you see, the stress levels are also increased. Let's check. So if you see, earlier it is like 70 megapascal approximately, now it is almost double because we increase the pressure value. Now suppose if you have your yield limit, or you can say allowable stress 100, so in that case you will see the red region. So it means that this portion is failing. So in that case, so you can do one thing, go to the geometry. So now if you want to do any specific change to your model, like if you want to provide the reinforcing pad, or you want to provide the respective weld, so you can use these spool options. So I will just explain quickly how to you can create a small pad. So what we can do, we can use this edge and we can give this a direction and we can project on this face. Okay, now we have projected. Now let's go and use spool option. Select this surface and then you can drag, just define the thickness like 5 mm. Okay, so now if you see, we have created a little pad, a 5 mm thickness pad on this. Furthermore, if you want to create a weld over here, so just go pull and you can here on a details you can use chamfer. Like you can define the dimension if you want 10 mm fillet like this. So now if you see, like we have created a pad as well as weld on that. Now let's go to our model and here you can just update the model. Okay, so likewise you just repeat the same procedure in order to perform your next simulation with your reinforcing pad as well as with your weld. So as I said that this is one of the advantages for your global model. Here on a local or any specific region of your model, or you can say your area of interest, you can perform or you can re-perform the simulation with a local detailing such as like a weld, a pad. Okay, and you can just simply repeat the simulation to get the more accuracy on a local area. So if you apply some pressure, if you apply frictionless support, let's try to generate mesh. Mesh is done. Now import load. Loads are imported. You have applied pressure, you have applied frictionless support. Now let's try to simulate the. So now if you see, our simulation is performed. Now if you see, the deformation is reduced. And check the local stress probe. Okay, now if you see, from 130 it got reduced to 100 megapascal. So 30 megapascal stress got reduced with the help of this reinforcing pad and with the weld. So you can further increase this thickness based on your allowable stress. If you have 100 mm allowable stress, so you can increase your reinforcing pad thickness. Okay, and you will achieve your accuracies for the simulation. Okay, so that's it guys, that's it from our side. So we explain you how to perform global analysis in first part, and then we also explain you how to perform the submodel. We also explain you how to do design changes when your model will going to fail, such as how to add a reinforcing pad, how to provide the respective fillet weld. Okay, so let me know your comments. I'll be there to help you. Please don't forget to subscribe our channel. We are adding so many valuable contents freely on our, and we also going to upload few more videos related to this pressure vessel modeling. In addition to that, based on your request, we will also add the requested videos from the viewers. So please don't forget to like, subscribe and share our channels. Thank you. Bye bye. Take care.